Alrighty, so this video we're going to move on to the next technique for analyzing circuits, which is called nodal analysis. Now last time we did loop analysis, which is the first kind of advanced way of analyzing a circuit. And with that, you would basically have a circuit. A lot of times there may be multiple voltage sources in the circuit, but not always. But a lot of times that would give you a hint that you may want to use a loop analysis technique. And you would basically assume a current in the different loops that are formed by your circuit and use one of Kirchhoffs' laws that says that the total voltage gained minus the total voltage dropped in a closed loop of a circuit must be equal to 0. So you would write out equations, one for each loop, one for each loop that you create, and it would be an equation for the various voltages. So if you gained a voltage by a voltage source, or if you dropped a voltage by a resistor, you add up all those voltages and you'd set it equal to 0. And then you would convert those voltages into currents by saying V is equal to IR. So when you need to calculate the voltage dropped by a resistor, instead of saying the voltage of that resistor, you would say the current which is on that resistor times its resistance. And then you'd be left with multiple equations with multiple unknowns, those unknowns being currents. And then you'd use your algebraic techniques to solve for those unknown currents, and then you could figure out the rest of the circuit. Well, now we're going to do something similar with nodal analysis, only it's kind of the exact opposite. Now what we're going to do is we're going to have circuits, and we're going to use a different Kirchhoffs law, this one which talks about the currents, and we're going to set up equations of current, convert those currents to voltages, and then use algebraic methods to solve multiple equations with multiple unknowns to solve for these voltages. So it's a very similar idea, but a different way of implementing the idea, and instead of solving for currents, we're now going to be solving for voltages. So, first thing you need to know is this form of Kirchhoffs law, which says, it's Kirchhoffs current law. A lot of times you see it abbreviated KCL. And what it basically says is, all currents coming into a node must balance the currents leaving a node. Okay, just a simple way of thinking about the law, and it makes sense. Say you have a circuit. Okay, here's my circuit. And I look at, and let's say this is a node right here. A node can be thought of as any location where multiple elements are connected. So here you have two different resistors are connected to each other, and that connection point I'm going to call a node. Of course, this green spot is also a node. This green spot is also a node because it connects the resistor to the voltage source. They're all nodes, but I'll look at the red one, and I'll say, okay, let's think about the current which flows through this circuit. Well, here's the voltage source. The current goes out the voltage source, hits the resistor, and then notice that current comes in and hits my node. Well, that current doesn't disappear. It must keep going, and in fact, it now leaves that node and goes through the circuit and just keeps on going. So we get our little loop of current. Well, what this law says is very intuitive. It says all the current that comes into a node must also leave the node. So if you had 2 amps coming in, you better have 2 amps leaving. You can't just save a bunch of current in some spot of a circuit and it doesn't leave. Nor can you gain a bunch of current all of a sudden. If you had a certain amount of current coming into a node, that same amount must leave. You don't gain it magically, you don't lose it magically. And that's all this law says. But what's powerful about it is it's going to allow us to set up these equations for the currents at these different nodes, which then allows us to make those current equations into voltage equations and then calculate voltages that we may want to know. So let's see how to do this. Let's take an example, and this type of thing, I can't just word my way through it. You have to see it as a worked example to see how to do something like this. Let's say we have this particular circuit. Now, what you're going to find is that with nodal analysis, unlike loop analysis, instead of a bunch of voltage sources, we're going to see current sources pop up. So if you're not used to what a current source looks like, it's an element that has a little arrow like this. So remember, this is a voltage source. That's voltage. Well, this is what a current source looks like. The arrow tells you the direction that the current is flowing, and it may have, 2 amp coming in or 4 amp or whatever it is. So this is just an element that can be placed into a circuit, just like a voltage source is an element or a resistor is an element. Well, now we have a current source. That could stand for some, this may be some big, huge electronic circuit. We're going to focus on a little bitty part of that circuit. And so we may show a current source, but that current source may, really be a symbol for a bigger part of the circuit that we're not going to worry about. All we know is that because of this thing, we know how much current flows right here. And that's what the current source tells us. Okay, so here's the example of the circuit we're going to use. We have a current source, resistor, let's say this should be good. We'll do a simple example first, not get too overwhelming. All right, and let's say this is, 2, this is 3 and 4. Okay, so nice simple circuit. I don't show a voltage source here, but there's some voltage. But I do have a current source, so I know how much current is flowing in this circuit, 2 amps. And I've got 2 different resistors sitting there. And what I may want to do is, again, I may want to be able to take this particular table and say, okay, I have a 3 and a 4 ohm resistor. For each one of the resistors, how much voltage is dropped and how much current flows. Okay. But what I'm going to do is I'm going to use nodal analysis to calculate it. There's a few things to remember when you do nodal analysis. First thing you're going to have to do is choose a spot on your circuit to be what's called the ground. And the ground symbolically looks like this. So it's almost like a voltage source, but it's got 3 little lines instead of 2. And where you place this symbol is going to determine this point of my circuit is defined to be 0 voltage. That's the ground. 0 voltage is there. Now, you're going to choose the spot on the circuit. You get to choose wherever you'd like. Because what's going to wind up happening is after you do all this analysis, the answers you get are going to be relative to the ground. So for instance, if you get an answer to the voltage of the 3 ohm resistor to be 7, well, what that really means is that the voltage dropped by that resistor is 7 volts more than the ground. So if the ground were actually 3 volts, but you assumed it to be 0, then all it means when you actually do a real analysis is you take the 7 you thought it was and you add 3 to it. So you could choose ground anywhere you want. If this is a real electronic circuit, what you would do is you'd use your little multimeter or something like that. Say, okay, where I thought the ground was, what's the actual voltage? It's 3 volts, okay. Then I take all the analysis I did, those answers I got, I just add 3 to the voltage of all of them. But what's important is to choose a place to be ground, because that's going to give us some information to allow us to solve different answers. Now what you're going to find is almost always you're going to choose the ground to be down here somewhere. And the reason that's good is because there's no elements down there to get in the way. All of the different parts are all connected there in some way. So you're going to find pretty much all the examples we do in this class, you're going to choose the ground to be down there like that. Okay, so after you've chosen a ground, then what? Next thing you want to do is label the nodes you're going to use to solve your problem. So how do you label nodes? Because you could, there's plenty of nodes, but you may not need all of them. I'm going to use green to label the nodes here. And I'm going to say, okay, notice where the current source is located. All right, I could choose this point to be a node if I want. But notice all that's there is this bunch of wire over here until I get to this kind of split off point. And so that wire is really nothing to me. So that's not a good place to choose a node, because really what is the node is all of this is all one big node. If you remember when we were talking about resistors in series and parallel, sometimes you'd have those supernodes, those bigger nodes, which is not just a single point, but maybe a whole line of wire is all one big node. So all of that is really a node, and so the way I'll label it is I'll say this point right here is a node, and I'll call that node A. Okay, where else can there be a node? This can be a node here. But notice, again, all of this is just wire. So really, all of that is the same big node. But this is the thing. Because I chose a ground already, the ground acts as a node. So all of this stuff, all of this, is all the ground. That's all the node called the ground. So I really don't have to call that anything. I can if I want, but you're going to find that really what's going to happen is it's going to be called 0. So instead of writing it down, I'll just not worry about it. So really, for this problem, there's only one node. What's the next step? Once you have all your nodes labeled and you've chosen your ground, then you want to figure out what are the currents that are coming in and out of the nodes. So we're going to use Kirchhoffs Law, the KCL law, that says all nodes have currents coming in and currents going out, and you get to choose how they are. Just like with loop analysis, we chose our currents to be going clockwise around the loop. That was just an arbitrary choice. We could have chosen them counterclockwise too. So I'm about to label a bunch of currents, and those currents can either be coming into or out of the node, and sometimes I can look at the circuit to see which way they're going. Sometimes I can't. That's the art of this, and it turns out it doesn't matter what you choose, because if you chose the wrong way, if you thought a current was coming into the node when really it was leaving the node, you're just going to get a negative sign when you solve for it. The number itself, the actual answer, won't be changed. So here in yellow, I'm going to show you what the currents look like. First of all, notice the 2 amp current source. I already know which way that current flows. So I have a current coming in of 2. That's easy. But now I have 2 other wires leaving that node. The wire moving downwards towards the ground that hits that 3 ohm resistor, and I have a wire moving to the right which hits the 4 ohm resistor. So there's going to be a current in each of those wires. Now, I'm going to assume that the current going downward, or for the 3 ohm resistor, is moving down towards the ground. Okay, I'll call that I2. I1 was this 2 amp current source we knew of. And then a third, I'm going to choose to leave going to the right, and I'll call that I3. Okay, so you look at your node, there's 3 wires hitting the node, so there's 3 currents. Here, one of the currents, I1, I already know its value, it's 2, and it's coming into the node. The other 2, I2 and I3, I don't know which way they go. I'm going to assume arbitrarily they're leaving the node. And so I just draw them, and I label them I2 and I3. And you would do this for every node in your problem. Okay, once that's done, now we actually go through and we do our equations. For each node, we're going to have an equation. So let's look at node A. That's the only node we have, but I'll write it just as if we have multiple. So the equation for node A, what do we have? I've got I1 is coming in, I2 is coming out, and I3 is coming out. So what I'm going to write is all the currents that come into my node are positive. All the currents that leave my node are negative. So I have I1 coming in, minus I2 leaving, minus I3 leaving, better be equal to 0. This is the KCL law. That's the law that says all the current that comes in must balance all the current that goes out. So current 1 is coming in, current 2 leaves, and current 3 leaves, and so if I add them all together, I better get 0. But I don't know necessarily what these currents are, so I'm going to try to convert them into voltages. So the next step is rewrite them as voltages unless I know the value of the current. Well, notice I know the value of current 1. That's the current source sitting there, which is 2. So I1 is already equal to 2, so that's done. But now I2, I don't know the value of I2. So this is when I use V equals IR, Ohm's law. I solve it for I get I as V over R. So everywhere I see an I, I'm going to replace it with V over R. Okay? But what V do I use? Well, this is what we have to see, and I'm going to flip the page really quick to show it. But when you have a resistor, and there's some current flowing through the resistor, the voltage dropped by this resistor is like saying there's some voltage over here on this side and there was some voltage over here on this side. So I had V1, I went through R, and now I'm left with V2. The voltage dropped is V2 minus V1, or V1 minus V2, either way. Okay, it's the difference between the voltages on either side. Because let's say I had 10 volts to start with, but my resistor ate up 2 of it. So I started with 10, I'm left with 8. So I'd take 10 minus 8, that gives me a change of 2. I would dropped 2 volts. So that's what I have to do here. This V is really the voltage dropped by the resistor. So I look, I2 is moving downward, so the resistor is the 3. What's the voltage on either side? Well, at A, I'm going to call it the voltage at A. I don't know the value, but I'm going to call it VA. So it's VA minus the voltage on the other side of the resistor. Well, the voltage on the other side of the resistor is this ground. And I already know the voltage there. That's 0 by definition. So it's VA minus 0. So that's the voltage dropped by my resistor. The voltage on one side minus the voltage on the other. So VA minus 0 divided by the R that the current went through, which is 3. And this is my I2. I just rewrote I2 as a voltage thing. I know the R, that's 3. So now my equation becomes, instead of equation of I's, it's equations of V's. Let's look at I3. That's the next one. I3, I also don't know the value for I3, so I'm going to do the same thing. Instead of writing I3, I'm going to write the voltage drop by I3 divided by the resistor. So again, we do the same thing. We start at A, so we have voltage at A, minus the voltage on the other side. Well, what's the voltage on the other side of the 4? Over here. Again, all of this is all the same node. This is all the ground, all of it. So the voltage over here, the right side, is the ground. So it too is 0. So again, I have VA minus 0 divided by the resistor. Well, for I3, the resistor is 4. And so now I'm done with I3. And now I set it equal to 0. All right, so there's my equation. Notice this equation only has one unknown sitting there, VA, the voltage at node A. Well, this is solvable. I can solve this equation. If this were a more complicated circuit, I may have more than one node, a node B, a node C, and whatever. And so I'd have to do all of the equations, and then I'd have multiple equations with multiple unknowns. I don't know VA, I don't know VB, I don't know VC. But here I just have one node, so I only have one equation. So let's solve it. What does this equation look like? Well, it's 2 minus VA over 3 minus VA over 4 is equal to 0. There's different ways of solving this. I want to get rid of the denominator. The fastest way to get rid of the denominator is to multiply by something that's divisible by both of these numbers, 3 and 4. So I'm going to multiply everything by 12. So 2 times 12 is 24. 12 divided by 3 is 4, so 4 VA. 12 divided by 4 is 3, so 3 VA equals 0. And now we see 24 minus equals 7A. So VA is 24 over 7. I now know the voltage at node A. And then from here, I could fill out the table. I could say, okay, well, if the voltage at A is 24 over 7, then the voltage dropped by the 3 ohm resistor is the voltage at A, the thing that I have written right here. The voltage at A minus 0, that's the difference between the voltage on this side of the 3 and the voltage at this side of the 3. That's the voltage dropped. So 24 over 7 minus 0 is 24 over 7. Oops, this is the current. 24 over 7. And the same for the 4. The voltage on this side minus the voltage on this side is 24 over 7 minus 0. And then to get the I, we take 24 over 7 divided by 3, which is called I2, and 24 over 7 over 4, which is called I3, and that's how we get these two values. So you see, to fill out the table is quite easy. The equations are sitting right here. That's how we get the I for the 3. This is how we get the I for the 4. What we had to do was calculate these VAs to get this stuff. Once we had the VA, we use these equations to get the I's and to get the V's. So, how did we do it? Let's go over what we did here. This circuit, we used nodal analysis to analyze it. In order to do it, the first thing we did was we chose a part of the circuit to be the ground, which basically means this area of my circuit I'm going to define to have 0 voltage. It may not in actuality. It might actually have some voltage. But I'm going to define it to be 0. So when I get all my answers, those answers are relative to 0. So I chose a ground. Once I chose a ground, I now define my nodes. So I go into my circuit. Where are all the nodes I need to worry about? And I label them. In this case, there was only one real node and the ground. So I don't count the ground as a separate node. It is a separate node, but it's called the ground, so it's special. So there was only one node I had to define, which is node A. At that node, what do? I show all the currents coming into the node, and I show all the currents leaving the node, and I label them. I1, I2, I3, I4, however many there are. Once this is done, now we set up our equations using KCL. And KCL says all the i's coming in are positive, all the i's going out are negative. I add them all up, set it equal to 0. Then the last step is take all those i's. If you know any of the values up front, because maybe like here you knew one of the current sources, then you fill in the value of that current. If you don't, then replace all the i's with V over R, where V is the voltage on one side of the resistor minus the voltage on the other side. Sometimes you're going to have a VA minus VB over R. Here, because we only had one node, it happened to be VA minus 0 over R, because the other side of the resistor was connected to the ground. Once this is done, you're going to be left with an equation that only has V's in it. Solve the equation for the V, and you have your answer. From there, you can answer whatever the question's actually asking you for. What do I do with this VA? Well, if I want to know the current on a certain resistor, I've defined that to be I2 or I3. I2 is the current on 3, and I3 is the current on 4. So if I want the current on 3, I just look. Well, okay, the current on 3 was called I2. And then here, circled in blue, I2 is VA minus 0 over 3. So I take my VA, subtract 0, divide by 3, I got a value. That value is what goes on my table for the I for 3. And likewise for 4. Once you have the I's and the R's, V is equal to IR. All right, I'll do one more example. In this one, we're going to show one that has 2 nodes in it. That way we can see how does that change things. So say this is our circuit now. Yeah, this will do. Let's let this be 2. This will be 3, 4, and 5. Okay, so let's do nodal analysis here. What do I want to find for this? Let's say, well, I'll leave that alone for now. First step, when we do nodal analysis, choose a ground. I'll choose it in red. Down here is my ground. So that means all of this stuff in red, all of this is the ground. Okay, next step, choose your nodes. I'll choose that in green. All right, where's a node? So here's my 2 amp current source. I follow it, and I get to this part where it splits. I'll call that a node. I'll call this node A. But then notice, if I keep going, I hit the 4 ohm resistor, and then there's a 5 ohm resistor. Well, what can I do here? I have a choice. I'm going to do this the stupid way, but it allows me to do it. I'll choose this node here, and I'll call it B. Okay. I'm calling this stupid because there's a faster way of doing things by combining the 4 and the 5. If I combine the 4 and the 5, then I'm left with this example. But I'm not going to do it, and so you can see what it looks like with 2 nodes. All right, so I've chosen my nodes. I've got my ground. Last step before I start writing equations is what are the currents? So I'll do that in yellow. Okay, well, for node A, I have I1 coming this way. I2, I'll choose to be going down this way, and I3 will leave to the right. Okay. Now what about for node B? For node B, I have a current coming in, but notice I already called that current on this branch I3. Right? The current that leaves A and goes to B, I've already called it I3, so I just call it I3. And then the current that leaves B, I'll say goes down, and I'll call that I4. All right, so for each node, I have all the wires are labeled with currents. Some are coming into the node, some are leaving the node. And notice what's important is this branch that has the 4 ohm resistor sitting there. Because all that's there is a resistor, that current that left A doesn't split. It stays as the same current, so the current that leaves A is the same value as the current that comes into B. That's why I call them both I3. I don't have to change it. All right, so now what? The last thing we do is math. Math says for each node, so I'll start with node A, we set up our KCL equations. That's the equations for I. So what do we have? I1 coming in, so he's positive. I2 coming out, I2 is negative. And I3 coming out, I3 is negative. Equals 0. So I1 minus I2 minus I3 is equal to 0. If I know any of these i's, I stick the number in. If I don't, I replace it with V over R. I1, do I know its value? I do. I have the current. So I1 is 2. I2, do I know his value? No. So I have to replace it with V over R. All right, so I start at A, so I have VA minus the voltage on the other side of the 3, which is the ground, so I call it 0, divided by the resistor is 3. And then I3, so I've got minus. Again, I don't know the value of I3, so I have to do V over R. V, I start at A, so VA, minus, what's on the other side of the 4? B, not 0. Notice, for the 4 ohm resistor, I'm going from A to B, not from A to ground. So I'm at A, and I'm going to B. So it's VA minus VB. And I divide by the resistor, which is 4. So I1 minus I2 minus I3 equals 0. All right, well, unfortunately, I notice there's 2 unknowns in this equation. So I'm not going to be able to get the answer with this equation. I'm going to have a second equation. But before I worry about it, let me simplify this down. I'll do the same trick I did last time. I'm going to multiply everything by 12 to get rid of the denominator, because 12 is common to 3 and 4. So 12 times 2 is 24. 12 times 3 gets rid of the 3 and makes it a 4, so minus 4VA. And then there's a 0 there, so he doesn't count. And I have 12 times this other thing. The 12 and the 4 cancel, leaves a 3. So I have minus 3VA and plus 3VB. Right? Because minus VA times 3 is minus 3VA. And then minus VB is plus VB times the same 3 is out there. So it's plus 3VB equals 0. And then, because I know I'm going to be doing this algebraic stuff, I'm going to get all the VA and VB on one side, all the numbers on the other. So I have minus 4VA minus 3VA is minus 7VA plus 3VB is equal to minus 24. There's my equation, and I have to leave it alone for now because I can't do anything more. Now I look at node B. What does his equation look like? Well, node B has I3 coming in minus I4 going out, equal to 0. All right, so I replace any of the i's. If I know the number, I plug it in. If I don't, I replace it with V over R. Do I know I3? No, I don't. So again, I go V over R. I went from VA, and I got to VB. So it's VA minus VB divided by the resistor of 4. Minus I4. I don't know the value of I4, but I'm starting at B, and I'm going to ground. So VB minus 0 over his resistor is 5. Okay, those are the two i's, set it equal to 0. And again, two unknowns in this equation. I can't solve it by itself. Let me simplify it down. Again, I've got these fractions. I don't like fractions, so I want to multiply by something that gets rid of all the denominators. What is a number common to 4 and 5? 20. So I'm going to multiply everything by 20. So when I multiply this first term by 20, it looks like this. 20 times VA minus VB over 4. The 4 cancels this, makes it a 5. So now it's 5VA minus 5VB. Oops. Okay. And then minus 20 times the second term. The 20 and the 5 cancel, makes a 4. So 4VB equals 0. All right, again, collect what I can. I've got 5VA minus 9VB is equal to 0. All right, and that's as far as I could go with that equation. Now what can I do? I've got two equations with two unknowns. I want to find VA and I want to find VB. I have multiple ways of doing it. I'm going to use Cramer's rule really quick. So let me make the three matrices, one for VA, one for VB, and one for W. So the W is the easiest. It's minus 7 and 5, and then 3 and minus 9. The VA is going to be minus 24, 0, 3, and minus 9. And the VB is minus 7, 5, negative 24, and 0. Okay? And now VA is determinant of VA over determinant of W. The determinant of VA was negative 24 times negative 9, which is 216, minus 0 times 3, which is 0, divided by the W, negative 7 times negative 9 is 63, minus 5 times 3, which is 15. So we get 216 over 48, which is, I believe it's 9 over 2. Yeah. So there's VA, done. VB, similar thing. Determinant of VB over the determinant of W. Let's look at VB. Negative 7 times 0 is 0, minus 5 times negative 24, that's 120, divided by W, and W I already know is 48. So now I have 120 over 48, which is 5 over 2. So now what do I know? I know the voltage at A, and I know the voltage at B. And this was nodal analysis. Same steps as the other one, only here I had 2 nodes to worry about instead of just 1. And so we had the extra bit of algebra at the end. The physics of it goes like this. You're given a circuit, you choose a ground. Once you've chosen a ground, you label your nodes. For each node, label the currents coming in and the currents going out. Once all of that's done, then you're going to write an equation for each node of KCL, which says all the currents coming in are positive, all the currents going out are negative, set it equal to 0. Take that equation of I's, any I's that you know the number for because you know the current source or something like that, then you plug the numbers in. All the ones you don't know the numbers of, you replace it with V over R. How do you do the V part? Well, you take the V at one side minus the V at the other. If your current is going from A to B, then it's VA minus VB over R. If your current is going from a VA down to ground, that is VA minus 0 over R. If you're going from ground to A, then you're going 0 minus VA over R. Okay, it's always follow the line, the direction of the current. That'll tell you where you were, that's the first term, minus where you were going, that's the second term. And then you divide by the resistor that's in between. Once you've done that, then you have a series of equations with a series of unknowns, just like with loop analysis. And at this point, that's just algebra. That's just the mathematics to get the answers at the end. So the critical part is setting up the equations. Now, nodal analysis turns out to be a much more powerful and much more used analysis technique for circuits than loop analysis. It's usually faster to do. It allows you to gain the information you're looking for more efficiently than loop analysis was or is. And so you'll see nodal, and you'll use nodal analysis more often. So because of this, we're going to spend a lot of time on it, and so you're going to get a lot of practice with it. But it's up to you to practice this stuff. I can do as many examples as I want. Well, that helps me because I learn it better. But you watching me, while it may inform you on how to do things, is not sufficient for you to learn it. You have to sit down with a pen and paper and actually go through the steps and do it yourself. I can't stress this enough because you're going to have a test. You're going to have homework problems where you actually have to work these problems out yourself. So take it seriously when I say practice these problems. Of course, I'm going to post a practice problem set on Canvas as I always do. I'm going to post another video coming up with example problems worked out. So we're going to see 2 or 3 more circuits. But you practice them. That way, when you do have a homework assignment, you know how to work them correctly. And when you see it on a test, you'll be able to do it. And more than that, the advanced techniques we're going to learn later on in the semester rely on your ability to do nodal analysis as well. Because what some of these other techniques are going to let you do is kind of modify or change the look of the circuit. But after you've done that modification, you still have to solve the circuit, which almost always is going to involve you doing nodal analysis. Now, you could use other techniques. You could use loop analysis if you'd like, but what you're going to find when you do this is you're going to rely a lot on nodal analysis. Everybody does, no matter what. So make a good use of your time right now to practice the heck out of it and get really, really good at it so that later on, when you're doing delta Y transformations or source transformations or other things, you can focus on those kind of aspects of the techniques, and the nodal analysis part at the end is kind of second nature. But anyway, I hope this is helpful. I hope this kind of gives you an idea of how to do this. Definitely practice the problems, open up the book, look at their examples, go on YouTube, watch other people, just search on YouTube nodal analysis examples and watch how other professors do them. There may be some little things that you're going to find where some people make the negatives positive and the positives negative. They have their negative signs backwards from me. All of that is meaningless. The point is the technique, the method. What's positive and what's negative, if they're backwards, at the end of the day will lead to the same exact number answer at the end. So don't worry so much if someone calls something negative that I called positive, because what you're going to find is everything else that I called negative, they're calling it positive now. But anyway, practice these things, get really good at this, and the rest of the semester will come fairly easy for you. So, until next time.